Sometimes we want to manipulate an equilibrium expression, and so we need to be able to understand what to do if we manipulate that expression. So one thing we can do is write a reaction in the opposite direction. So if we simply reverse the reaction, then the equilibrium constant is simply the reciprocal of what it was. If, however, you decide to change the numbers or the coefficient by doubling or tripling everything in the balanced equation, then what you have to do to the equilibrium constant is raise the equilibrium constant to whatever it is you multiplied through. For example, our dinitrogen tetraoxide example here, we've got an equilibrium constant of 0.212. If I write the reaction in reverse and start it as 2 nitrogen dioxide going to dinitrogen tetraoxide, well, to get the equilibrium constant, I take 1 divided by 0.212, and I arrive at 4.72. So you can see the same molecule is going to dominate at equilibrium, that being the N2O4, regardless of how the reaction is written. It's just the meaning of the equilibrium constant is changed to indicate that. So again, by writing the reaction reversing the reaction, we take the reciprocal of the equilibrium constant. Now, if I go back to the original reaction and decide I want to double everything in the balanced equation, like this, then what you can see is I take the equilibrium constant and raise it to the power of 2 in this case because I doubled it. If I had tripled everything, I would have raised it to the power of 3. Now, one of the reasons we do that is we want to be able to use known chemical reactions to determine an equilibrium constant in something we may not necessarily have data for. And so what we do is we can take known chemical reactions and write new reactions from them and be able to predict what the equilibrium constant for that is. In fact, this is an extension of Hess's law, which you'll recall from thermochemistry in first semester. So whenever you take two chemical reactions and combine them, you multiply their equilibrium constants together. So let's take a look at this reaction here involving hydrofluoric acid and I believe that's oxalic acid. And so we've got two known equilibrium expressions for those two acids. And what we want to do is we want to find this equilibrium constant for this reaction we don't know. So what we do is we begin to look and match up things that we can identify in, in the reaction. So here we can see we've got HF, don't know what's going on. We've got HF right here. We've got HF right here. H2C2O4 actually appears over here, so we've got to write this reaction in the opposite direction because what we want to have is this molecule on this side when we combine these reactions. So what I'm going to do is I'm going to reverse the reaction here and say 2H plus C2O4 minus 2 goes to H2 C2O4. And the equilibrium expression for this is now 1 over 3.8 times 10 to the minus 6. Now the other thing we need to do is we've gotten rid of this form of the equation. We've written it in reverse. Now we have to deal with the fact that the HF does not have the same coefficient here. So what we have to do is take our original HF equation and multiply everything by 2. 2, 2, 2. That way the coefficients match up when we combine the equations. And since I did that, I have to take the equilibrium constant and raise it to the second power because I doubled everything. And so when I do that, I can calculate the equilibrium constant here, K. It's going to be equal to 6.8 times 10 to the minus 4th quantity squared all over 3.8 times 10 to the minus 6. So I combine those two equilibrium constants to arrive at something I don't necessarily have a value for, but now I can predict what it is. And so that's how you can manipulate equilibrium expressions.